In this video, we will discuss the effect of our reinforcement concept on the fracture toughness, based on the results of the experiments described in the previous video. Let's start with the Mode 1 behavior. For the baseline specimens, the force displacement curves look as one would expect, with linear elastic behavior over here up to the maximum force, and then more or less stable crack growth with some stick-slip behavior. Now let's include the curves for the reinforced specimens, shown in orange. The reinforced specimens reach roughly the same maximum force, but do not exhibit a large load drop immediately afterwards. Instead, the force remains roughly constant until the displacement is increased considerably. This can be explained by the effect of the tabs. As can be seen in this image taken during the test, the tabs remained connected to both sides of the crack face and acted as crack bridges, at least until the displacement was increased far enough to fracture the tabs themselves. The result is that for the reinforced specimens there was a much more pronounced R-curve behavior, with the propagation toughness being significantly larger than the initiation toughness. Comparing this to the rough location of the tabs, we see that the toughness increased as the crack propagated through the reinforced region, and that in some cases the toughness remained high even when the crack tip had already passed outside of this region again. Comparing the baseline and reinforced fracture toughness, we see that the initiation values are almost the same, with the reinforced value being slightly lower. On the other hand, the propagation toughness is increased by 77.6% for the reinforced case. Now, let's look at the Mode 2 results. Again, we see the expected force displacement behavior. Initially, the material is linear elastic until the crack starts growing. Then the force remains roughly constant while there is stable crack growth. The sharp increase in force beyond 6 mm of displacement in this region is caused by the crack tip propagating past the loading pin. Now, including the force displacement curves for the reinforced specimens, we can see that there was very little difference in behavior between the baseline and the reinforced specimens. And also, when looking at the R-curves, we see little difference. The explanation for this lack of reinforcement effect can be seen on the fracture surface of the specimens. A typical fracture surface for one of the reinforced specimens is shown here. On this surface we can clearly distinguish three regions. The first region is the pre-crack region, where the Teflon insert was used to initiate the crack. The second region is the reinforced region, where the tabs and slits were located. We can clearly see the tabs on the surface, for example here and here, as well as the points where they passed through the slits to connect to the ply below the surface that we can see here. For example, in this location and in this location, and here we can see where the slits were located. Finally, the third region is the post-reinforcement region, where there was no interlocking of the plies. From the fracture surface we can deduce the path taken by the delamination, which explains why the tabs did not affect the fracture toughness. Let's consider the crack path around a single tab and slit, shown schematically in the figure on the left. The tab starts in the top ply, where it is attached to the surrounding material. It then passes through the slit and ends at the indicated free end. The delamination will initially progress in the plane between the ply containing the tab and the ply containing the slit, as indicated. Note that the ply containing the tab has been made partially transparent to aid visualization. The desired crack path would be for the delamination to remain in this plane, growing under the tab as indicated by the dashed arrow. In this case, the tab would bridge the delamination, increasing the fracture toughness. However, from the fracture surface it is apparent that the delamination instead jumped over the tab, as follows. Therefore, in the actual experiments, the tab did not remain attached on both sides of the delamination and therefore could not act as a bridge. A final interesting comparison is to look at the effect of the delamination happening at a 0-45 interface rather than along a unidirectional interface. For this we can compare our data with that previously published by Narducci and co-workers. We can see that for Mode 1 the toughness of a 0-45 interface is considerably higher than for a unidirectional interface. And the same holds for a Mode 2 delamination. In conclusion, we found that the reinforcements, at least as currently designed, did not affect the Mode 2 fracture toughness, but they did increase the Mode 1 propagation toughness by 77.6%. The next video in this series will examine the consequences of this for the compression after impact loading.